All right, our second part of the Unit 4 video, it's going to be on soil formation and erosion, and then soil composition and properties. So hopefully you can remember back to class when we talked about soil, it's composed of 3 different particles: sand, silt, clay. So I want you guys to take a second, pause the video, and I really hope that people are actually pausing the video and testing their knowledge, because it doesn't do any good just to watch through the videos. There was a great quote, I believe it was Aristotle, who said, "You learn more by doing than you ever do by listening." So the more you actually perform these tasks, the more likely it is to sink into your brain. So go ahead, take a second, pause the video, and see if you can remember which of the 3 is the largest, which is the smallest. All right, when you guys come back, hopefully you guys find that sand was our largest particle, clay was our smallest, and silt is probably closer to clay than it is to sand. So sand is by far the largest particle. It has those really jagged edges to it. Clay is going to be very, very tiny. It's microscopic, and it's almost perfectly spherical. Maybe if you look at it under a microscope, you'd see some variations, but it's a super tiny spherical particle. The silt is going to be kind of closer to the clay size, but still a little bit jagged with it. And that's going to be important. The size of the particle is really important for the properties of the soil that contains them. So when we go through and look at the next slides, we want to know what the relative composition determines its soil properties. So what I need to know is, what does relative composition mean? Relative composition is the percent versus each other. So if I say that I have a soil that's 48% clay, 12% sand, I know that the remaining particle has to equal to 100%. Because when I talk about relative composition, it's just related to those 3 particles. So 48% and 12% equals 60, right? So I know then I have to have 40% silt. That's going to give me certain properties compared to a different soil that might be, say, 12% clay, 40% sand, and 48% silt. All different proportions are going to allow it to have different properties. So the first property we look at is its water holding capacity. What do you suppose water holding capacity means? Go ahead, pause the video, think through it, try to break it apart, figuring out what it is. So when you look at water holding capacity, it's pretty self-explanatory. It's how much water it can hold on to and retain within its structure. Why is that important to us? That's what's going to determine nutrient availability. It's going to allow plants to grow, all those different things, because plants need water to grow. Not only do they need water, but the nutrients dissolve into that water. So it's a mode of transporting nutrients as well. If soil has good water holding capacity, meaning I can hold X amount of water in it, and that's greater than a different soil that's only able to hold a little bit of water, my plants are probably going to flourish more in that higher amount of water holding capacity than in the previous one. So that's what it is and why it's important. Porosity and permeability. Go ahead, take a second, pause, see if you can remember what those are. So when we talk about porosity and permeability, porosity is the amount of empty space in a soil. Remember when we talked about sand, it's a really, really big particle with jagged edges. So because of that, there's a lot of empty space in between the particles. That empty space is the porosity. The permeability is linked to that because porosity determines permeability. Porosity is the empty space. Permeability is how well water flows through it. So the higher the porosity, the quicker the water is going to go through. So when we look at this, why are these 2 things important? Again, we don't always want roots to be exposed to water. They need to have the ability to allow gases to diffuse out of the roots. If we have them submerged in water all the time, that's going to cause the roots to die and rot because there's no gas exchange happening. So we need porosity because we need empty space in our soil to allow for water holding capacity. And we also need the water to be permeable, the soil rather, to be permeable, so the water doesn't just stand in the soil, it's able to flow through the soil. As it flows through the soil, that's what's bringing the nutrients from the top down to the bottom. So we have different physical, chemical, and biologic tests we can determine soil quality with. So think about a physical test you could run to determine soil quality. If you remember back when we did that soil lab, the physical test is where you separate it into its components. Remember how we put it in the graduated cylinder, shook it up with a little bit of soap, and it separated out into its particles? That's a physical test you can do. An easier way to do it is to use a series of screens. If you use a series of screens where the hole size, the size of the holes in the screen, are big enough to let everything but sand in, that will tell you how much sand you have. Then you pass it through another screen that has a smaller set of holes. And that smaller set of holes is going to let everything else except for silt through. And then finally, you put it through an ultra fine screen to allow the clay to come out. That clay then, again, it's super, super fine there with it. And really, you don't even need to separate the clay out, because by separating the sand and silt, you've left yourself only with clay to begin with. But again, by using a series of screens, that's going to separate it into its component parts. And that's going to determine the physical characteristics of the soil, the composition of sand, silt, and clay. Biologic test we can do is test for different life forms in it, bacterial composition, amount of worms and microorganisms that are in it. Those would be our biologic tests. We need those microorganisms, we need the bacteria to help with the breakdown and decomposition to release nutrients. The chemical tests, those would be things like pH, nutrient levels. Remember how we tested for nitrates, phosphates, and pH in that lab? Those would be the chemical tests. By doing all these different tests, we can tell what quality of soil we have. Not only the type of soil, but also the quality as far as growing capacity. The porosity and permeability we can test with a physical test. Putting water into it to see how much water the soil can hold. That's the water holding capacity. Seeing how quickly the water can drain through would test permeability. All those are tests that you can run to see whether the soil is suited for what you're trying to grow. If you know you're trying to grow a crop that needs a lot of water and needs constant exposure to it, you would want to limit your permeability as much as you can. So you'd want a physical test done to try to maximize or see if there's enough clay to increase the water holding capacity. You'd still want it to be high in nutrients though, and you'd want those microorganisms to be present. So that's the reason why we're doing these tests. And again, to determine what type of soil you have, the best physical test is to separate the components and find where it falls on the soil texture triangle, because different plants need different types of soil to grow. Also, different applications need different types of soil. If we're lining a landfill or a pond, we want it to be high in clay. If we're doing farmland, we want it to be a loamy soil. That loamy soil is the perfect mixture of all the particles to give good porosity and permeability while still retaining the nutrient holding capacity and the water holding capacity. You always want a little bit of clay, because don't forget, when we talked about clay, clay has that negative charge to it. So the negative charges on the outside help to hold those micronutrients, the sodiums and the calciums and things like that we need. Remember how we linked it back to acid rain? As those micronutrients are needed, they usually adhere to the clay particles. But when we have acid precipitation happening, now those H plus ions that are part of that acidic water adhere to the clay particles, blocking the micronutrients, which then kills the plant life off. So again, if you guys don't remember how to use this triangle, I don't think they're going to ask it on the AP exam this year, just because they assured us that there wasn't going to be any graphing. This is graph interpretation though, so they may ask it. It's still eligible content. What you want to look at is the direction the numbers are written is the axis that you're looking at. So let's go back to my soil that was 42% silt, 40% sand, and 18% clay. So the first line I want to draw in is my clay line. I draw that in where 18% is at. So somewhere around in here. Right? Then my next line that I'm going to put in is my silt line. And if I look, oh, I'm sorry. I actually drew this in the wrong way already. So my clay axis is actually over here, and it's going horizontal. So at 18% clay, I'd have my line go across like this. And note again, direction of the numbers determines which way I'm writing my lines. So my next line is going to be for the silt, 42% silt. So I'm going to go here where about 42% would be at. And then my final line is going to be my sand line, which is 40%. And again, I wasn't very precise in where I'm putting my lines, but I know that where the three intersect, that's the type of soil I have. So I'm likely to have a loamy soil. This soil is great for farming. Great for farming because I'm getting that nutrient holding capacity of the clay, I'm getting the drainage of the sand, and I'm getting that water holding capacity of that silt kind of taking up some of the spots of the sand. So I'd have a fairly moderate permeability, good nutrient holding capacity, while still having water holding capacity for it also. So when we look at soil itself, how's it formed? It's formed through a couple different processes. The first thing that needs to happen is a physical and chemical weathering. Physical weathering is done by wind and water. It's where the rock starts to chip and break away. It's releasing minerals out of that big piece of rock. With chemical weathering, this is where it's done by acid. If you remember back to succession, we said primary succession takes such a long time because the soil has to be formed first. That soil is formed by a mixture of the wind and water hitting and breaking small little pieces of mineral out of the rock. It's sped up when the lichens start to inhabit it, and that acid starts to dissolve the rock quicker. When it dissolves the rock, it's releasing the mineral components. We have this done by either biologic things excreting acid, or we also have it through acid precipitation. Okay, as that mineral component is released, it starts to build up, it's deposited. So the deposition is where that mineral component keeps on building up, building up, building up. But just having it in this one area, this will build up in like the cracks and crevices of the rock. That does a little bit for the rock itself to support life. But when we're looking on building at a large level, that's where erosion is going to be important. That wind and water now is going to carry those particles and collect them in other places. So we have soil being formed through physical and chemical weathering first, that deposits those mineral components onto the surface. Those deposited mineral components can then erode and wash away. Difference between erosion and weathering, they're not the same thing. Weathering is the breakdown. Erosion is the transport. So soil formation is all about breaking down, transportation, and then deposition. So we have to have the mineral component broken off the rock, transported elsewhere, and then deposited and allowed to accumulate. Once we do that, then we can start to support life. And if you think back to when we talked about that deposition, it usually stacks it up in a soil profile. And the soil profile is a series of horizons. Try to pause the video, see if you can remember what these horizons are. We can see that we have a horizon here. Do that with yellow here. We have a horizon right here, another one here, another one here, and then down below that. So see if you can remember what the surface horizon is, the next horizon, down, and down are. So go ahead, take a second, pause the video, see if you can remember those. All right, so this first horizon that you guys did, hopefully you guys remembered. Let's see if I can get this to work. Oh, I don't know why I brought up the keyboard. So our first horizon is the O horizon. The O horizon is not true soil. Make sure you note that. It's not soil. The O horizon is just organic material, and that's why it's called the O horizon. So the O horizon is the organic material or the humus on the surface of the ground. This grass that's out there, I have to mow my grass later today. As I mow that grass, some of those little fronds of grass are going to fall down into the yard. As it falls down to the yard, they rot and decompose. As it's partially decomposed, that's the humus. So leaves fall, grasses fall, plants die, animals die. That's what creates that O horizon. This is going to be super rich in nutrients. All right, then when we go down to the next level down, hopefully you guys remember that that's going to be the topsoil layer. O horizons don't exist in every soil profile. But if you have a lot of plant life, odds are you're going to have an O horizon. Usually in the least biodiverse biomes like deserts, those don't have an O horizon. But in forests, you're almost always going to be likely to have the O horizon. In grasslands, almost always going to have the O horizon. So when we look at our A horizon, that's our topsoil layer. This is the first true soil layer because in order to be called soil, it has to be a mix of organic and minerals. That's the reason why the O horizon is not a true soil horizon. It's not true soil because it's only organic material. Here we have the organic material now mixed with some of that mineral component that was eroded away from the rocks. It's going to be richer in organic material though. It's going to be high organic, low mineral. So it's called topsoil because it's at the top of the profile. That's the best part to grow our crops in. So as you see, we have a lot more roots happening in the picture here than there are further down. The roots tend to be really thick in that topsoil because that's where they're gaining their nutrients. The A horizon is also called the zone of leaching because all of those minerals are going to go downward as the water flows through. So remember how we talked about the water percolating downward or the permeability allowing the water to flow downward. As that water flows downward, it picks up the nutrients and minerals, mainly the minerals, and carries them further into that soil profile. If you guys remembered in class, we actually put another horizon here called the E horizon that was kind of like a grayish color. That's the really heavy mineral component of the minerals that washed out of the A horizon. After the A horizon, though, the E horizon is not in all soil, so that's why I didn't include it. After that, we have the B horizon. That's our subsoil layer. This is going to be extremely high in minerals, but low in organic material. We can see we don't have many roots here because there's not a lot of nutrients for the plants to grow. A lot of minerals, but not a lot of nutrients. So as that water flows down from the A horizon, it's depositing those minerals into the B horizon. So they call it the zone of accumulation. And then down below that is the C horizon or the parent material. That's where the bedrock that kind of first started breaking apart to form these soil profiles started to happen. So if we look at the age of the soil, take a second, pause the video, and make a prediction on the age of these different horizons. Which is the youngest, which is the oldest. So hopefully you found that this was the oldest, this was the youngest. Now on the AP exam though, you would have to explain that. So take a second, now that you know that the oldest is the C and the youngest is the A horizon, explain why it works that way. So your explanation should have centered around C is the oldest because that was that bare exposed bedrock. It began to physically and chemically weather. As it physically and chemically weathered, it released minerals. Those minerals then allowed for plant matter to start growing. As the plant matter grew, the minerals that were in the soil started to leach downward and form the B horizon. The A horizon is that organic material mixed in with the minerals. So that's the newest soil that was formed because it required plant life to have be established before you can form that A horizon. So test for learning now. This section is done as well. So we're going to look and see if you guys can describe the characteristics the characteristics of soil and the formation of soil. Can you describe how it's formed and the different characteristics it has? Can you also describe similarities and differences between the properties of the different soil types? If you can't do that, make sure you guys go back or rewatch the video because we covered all those in this video. So I hope you guys are enjoying these videos. I hope you're getting stuff from them. If you're not, you don't have to watch them, but I do suggest either watching these or the YouTube videos College Board is putting out. I suggest watching both of them, but if you have to watch one or the other, lean more towards the College Board videos. They're much smarter than I am.